Okay, cool. So let's get started. Today we will talk about how to compute cameras from a given fundamental matrix. And we will discuss the calibrated case where the fundamental matrix can have the form of the essential matrix. And then we will talk again about the 8-point algorithm with respect to the essential matrix, the 5-point algorithm, which is a minimal case to solve for essential matrix, and how to compute cameras from the essential matrix. And in the end, we will talk about a deep learning-based method for relative camera pod estimation. Okay, so last week we defined the two-view structure for motion problem, where we are given two images with corresponding points between them. And the task was to compute the 3D points and the camera matrices such that the 3D points are projected to the corresponding given 2D correspondence cell. And mathematically, we formulate the problem as follows. Given two sets of corresponding points, xi and xi bar, we want to compute camera matrices P1 and P2 and the 3D points set of capital Xi, such that the 3D points are projected to the corresponding 2D points with the camera matrices that we output. And we showed that we can get a reduced formulation from two sets of points xi and xi bar. We just need to compute the fundamental matrix such that it holds that xi bar transpose fxi equals 0. And that actually solves for the camera matrices without requiring the 3D points, because from the fundamental matrix we can extract cameras, and then as a second step we can triangulate the points, and overall we got a closed form solution for a very complicated problem. So now we will talk about how to extract camera from F. So now we have the fundamental matrix and we don't have the cameras. So we want to get two cameras that are consistent with the fundamental matrix that we currently have. Okay, so again, as we assumed last week, we assumed that P1 has this canonical form of identity and 0, and P2 is in a general form of A and T, where A is a 3x3 matrix. And we want to calculate A and T such that the fundamental matrix has the following form. Okay, so the claim is that P2 can be formulated as follows, where the 3x3 part adds this form and the vector part adds this form, and V and lambda are just free coefficients. V is a three-dimensional vector, and lambda is just a non-zero coefficient that we can choose freely and still get the correct fundamental matrix. Okay, so that's the claim, and now we will show why this is true. So assume that we have a general 3D point capital X. Then let's look what are the projections of these 3D points to the two images using the camera matrices. So first we project capital X to camera 1 to get X. So we have I times, this is P1, we have I times capital X plus 0 times 1. So we just get capital X. And for X bar, it is a bit more complicated, but same idea. We multiply P2 by the homogeneous representation of the 3D point, X and 1. So we got the 3x3 part multiplied by X plus lambda E2 multiplied by 1. So that's a combination that we have, and both of them are defined up to scale. So if I want to verify that every two corresponding points are consistent with the fundamental matrix, what do I need to satisfy?
X bar f x equals 0.
Yes, exactly. So we just write our equation for the fundamental matrix with x bar transpose fx which actually equals to X transpose F transpose X bar. That should be 0 for every such 3D point that we used. Okay, so we just assign X to be capital X, and we assign X bar to be this term from before. And now we just need to open this term, and we get three monomials, which are actually three scalars. So the first one is resulted by multiplying X transpose F transpose with this part and X. The second one is resulted by multiplying this part with the epipole 2 B transpose times X. And the third part is just multiplying this with lambda E2. So we get three terms. But first note that these two terms contains F transpose epipole 2. And we know that epipole 2 is the null space of F transpose. So these two terms are just 0. So we are left just with the first term. And now if we rearrange it, so instead of X transpose, capital X transpose, F transpose, we write F capital X transpose. Okay, and in this term, we just replace the cross product matrix of E2 multiplied by the vector Fx to be just the cross product of epipole 2 with Fx. But what we have here is just have this following form of a dot product of A with the cross product of B with A. And the cross product of B with A is orthogonal to both B and A. So it's orthogonal to A, and the dot product between vector to a vector that is orthogonal to this vector is just 0. So we got 0 as required. Okay. Any questions about this slide?
Yes, I have a question. It's like on the second step, where you replaced X with capital X and X bar with like that expression on the right, you could do that only because it was up to scale, right? But because of the 0 on the right side, we could do that.
Exactly, because if you multiply this equation by scale, and the result is 0, then the scale doesn't matter. You can just multiply by any arbitrary scale both sides of the equation. It's just an homogeneous equation. So F is defined up to scale, X and X bar are defined up to scale. Everything is defined up to scale. So you can just choose the scale arbitrarily and get what you want. Okay. Okay, cool. So let's see a complete example for the two-view structure for motion problem and how it's being solved. So we are given two images with point correspondences between them. We calculate the fundamental matrix between the views using the 8-point algorithm. Then we extract the cameras as we showed now, and we use triangulation to triangulate the 3D points from the known cameras and the point correspondences. And on the right, you see what we got, which is actually not looking so nice, not as we expected it to be. And the reason is that projective reconstruction has this ambiguity of general homography that can really distort the reconstruction. So it doesn't preserve angles and ratios between segments. And usually what we would like to have is an Euclidean reconstruction. Okay, where for Euclidean reconstruction, the only ambiguity is similarity transformation that actually depends on the coordinate system, the general scale, general rotation, and general translation. So that's what we have now. And the question is, how can we go from a distorted reconstruction to an undistorted reconstruction? Okay, so there are actually three options to do that. One is to do it explicitly. If we have some prior knowledge on the scene, we just have to apply our knowledge um, on the homography, such that the homography will make our knowledge will make our solution to satisfy what we know about the 3D scene, like angles and line ratios. But this is kind of a manual work, and usually we would like to have something that is more automatic. And option two is just to assume some assumptions on the calibration matrices, and then find the homography automatically. This is called self-calibration, but we will not talk about it today. And the third option that we will discuss mostly today is to start over and use the non-calibration matrices K1 and K2 to reduce the ambiguity level and solve a different problem that is called the calibrated structure for motion problem. So we will talk about option 3 and define the calibrated structure for motion problem.
Can you explain again where this ambiguity of homography came from?
I think we mostly showed it last week, but if you have a solution to this problem that we define here, you can just place an homography and homography inverse here between P1 and Xi, and the same homography between P2 and Xi here, and this cancels, but so we can always do that. But then this homography defines a new solution of this homography times your points. And so it can, if it's not a similarity transformation, it can just distort your reconstruction a lot.
Yoni, I have another question. So you just showed us the form of P2 that satisfies this constraint on the next slide, right? And
Yes.
this was only the one of good examples, like one of many satisfying matrices, right?
Mhm. Yes.
And
Yeah, the homography that you choose actually related to these 4 degrees of freedom that you have here. So it's not all the degrees of freedom because we already chose P1. So in general, you have 15 degrees of freedom for homography, and we already chose like up to scale. So we already chose 12 when we chose P1, and so you have additional 4 degrees of freedom here, including the scale. So we have 16 degrees of freedom including the scale, and that's actually what you choose here. Like 12 here, and we have additional 4 here.
okay.
Just actually show you this also includes the distortion. Like you have a specific set of 4 numbers for V and lambda that will give you an undistorted reconstruction, but it's not so easy to search for them.
Yoni, how do you choose V again?
How do you choose what?
The parameter V.
So here you can just so every V will be correct. So if you don't know anything about the calibration, you just choose it randomly and you get correct matrices, but then probably your reconstruction after triangulation will be distorted as here. So that's the problem with projective structure for motion. In general, your reconstruction will be distorted when you use fundamental metrics and triangulate point correspondences.
Okay, and one more question about the second option with self-calibration. Are we going to discuss it in during this course?
I'm not sure. I think last year we did not discuss it because we did not have enough time. Maybe we will enter it at some of our lectures later, but I'm not sure
I think we don't have it in the plan yet now because we don't have time.
Yes, but we should keep it in mind if we have like free slot in some of our optimization series, maybe we can discuss it. It's actually an important part because without it, you cannot really use the fundamental metrics for reconstruction. You always need to get essential metrics for practical applications.
Thank you.
Okay, so what can we do if we have the calibration matrices? So in that case, recall that we have point correspondences and we want to find P1, P2, and a set of 3D points that satisfy what we want about the projection of the 3D point using the solved cameras. But remember that camera metrics can be represented by a calibration matrix multiplied by a 3x3 rotation and translation. So this is another 3x4 matrix, and the calibration is a 3x3 matrix. Okay, so that's what we have if we had the solution. So what we can do is just to multiply the first and the second equations by K1 inverse and K2 inverse respectively. And therefore we get for the first equation on the left side we get lambda I K1 inverse times multiplied by xi, and on the right side K1 is cancelled by its inverse, so we are left just with R1 T1 multiplied by xi, capital Xi. Okay, so we just multiplied by K1 inverse the first equation from both sides. So we can do the same thing for the second equation, where in this case you multiply by K2 inverse. And we get the following two equations. And now we can define yi to be ky inverse times xi, and yi bar to be k2 inverse times multiplied by xi bar. Okay, so note that yi and yi bar are just known numbers because we know the correspondences and we know the calibration matrices. So we just get a new set of correspondences, yi corresponding to yi bar, which we know the correspondences, and usually they're called normalized point coordinates. And then the task now is not to find a general matrix like the original structure for motion problem. In this case, we know that the cameras should have the following form of a rotation matrix in their 3x3 part and translation vector. And we need to find this such that this spatial camera projects the 3D points to the corresponding normalized coordinates. So we actually got a new problem, which is called the two-view calibrated structure for motion, where we're given two sets of corresponding normalized points, yi and yi bar, and we need to compute camera matrices, which here we denote by P1 tilde and P2 tilde, and 3D points, such that P1 tilde times multiplied by capital Xi is yi up to scale, and P2 tilde multiplied by capital Xi is yi bar up to scale. So here we have two normalized point correspondences, and we need to find P1 tilde and P2 tilde and Xi, such that Xi will be projected to the corresponding normalized points.
And this is under the assumption that you know the calibrated matrices, right? And you
Yes,
didn't use this assumption before.
Right. That's the assumption here. Basically, it's, if we think about practical application, usually it's a reasonable assumption, because today most of the cameras and the phones record some information about the calibration of the cameras. Like if you open a JPEG file, you can usually see some information about the calibration, which can help you to find a rough estimation for the calibration matrices. but it will be less accurate than accurately measuring the calibration matrices. More questions about the definition of this calibrated structure for motion problem? Okay, so like in the projective problem, we would like to simplify our cameras or our reconstruction such that it will be simpler to work with and develop the fundamental, and which we will call it later essential metrics. So again, we can just use choose our homography to be the following homography. And then if we multiply the homography from the right by P1 tilde, we get P1 tilde multiplied by this homography. So we get R1 multiplied by R1 transpose, which is an identity matrix, plus T1 multiplied by 0. And so we'll just get an identity matrix. I mean, okay, yes. And then we can multiply R1 by minus R1 transpose T1. So R1 is canceled and we get minus T1 plus T1. So we get minus T1 plus T1, which is 0. So we get this I and 0 for P1. And we multiply P2 by the same homography. And we just get the following solution, where this part is, the 3 by 3 part is still a rotation matrix, because the multiplication of 2 rotation matrices is still a rotation matrix. So we just got a new solution for the calibrated structure for motion problem using the multiplication by this homography. So we can just work with this to assume that our cameras are on this spatial form. Okay, so I have 2 cameras, P1 tilde and P2 tilde of this form. So what is the fundamental matrix between these 2 cameras? Can someone remember? Just show the closed form. Given cameras, we know how to extract the fundamental matrix between them. Can you remember?
It's the E2, the cross matrix of E2, the epipole 2, times R.
Yes, exactly. Or if we can just write the cross product matrix of T multiplied by R in this case, which is also true that this is the epipole point. So that's the form for the fundamental matrix in this case. Okay, so what's special about this matrix? First, it has a special name. It's called the essential matrix. And another interesting property is that it has only 5 degrees of freedom instead of 7. Can someone think of why it has only 5 degrees of freedom? How many degrees? Sorry, what?
It certainly has something to do with that R is a rotation matrix, so the term is 1, the norm.
So how many degrees of freedom a rotation matrix has?
3.
3.
Yes, exactly. So the rotation matrix has 3 degrees of freedom. And how many degrees of freedom this T has?
Also 3.
Also 3, but remember that
Up to scale.
Find up to scale, yeah. So we have 2 degrees of freedom for T actually, and we get in total 5 degrees of freedom.
Can you explain again this up to scale part? So I understand that T is a translation vector, but up to scale, you mean that we can go in the direction of this T up to scale?
Okay, I have 2 solutions. One is algebraic one. We want a fundamental matrix or essential matrix to map a point to its corresponding line such that the corresponding line is on this point. So that can actually algebraically be formulated by x transpose f x bar transpose f x should be 0. So this equation, for this equation, you can just scale the fundamental or the essential matrix for any scale, and it will still be satisfied. So that means that it doesn't have any, you can just use any scale that you want to multiply your fundamental metrics, and it will still be valid. The second intuitive explanation is that since you cannot choose the scale of your coordinate system without having some prior knowledge on the units that you use, it can be meters or it can be kilometers. So the translation vector just sets the scale of the distance between your cameras. So without knowing the units that you're working with, it's just an arbitrary scale.
Okay, the first explanation I understood better.
Okay, yes. Cool. I can elaborate more about the second, but if you want, but maybe we can continue and discuss it later. Okay, this is still a fundamental metric, so its determinant is 0, but unlike the fundamental metrics, it has another interesting property. Its two non-zero singular values should be equal. Okay, it has 3 singular values. One of them should be 0, and the other 2 should be identical. Okay, but remember that we don't have the camera. So basically, we want to have point correspondences and to estimate the essential metrics from the point correspondences that satisfy this equation. Okay, so again, we know the normalized point correspondences, and we write, like in the fundamental metrics, the following equation, and open this equation to get 9 elements from these equations, where we only know the point coordinates and we don't know the essential metrics entries. So we get a linear equations in the elements of the essential metrics. So if we have n correspondences, we get n equations, n linear equations that can be expressed by the matrix multiplication A with V, that should be 0, where V is a vector of our unknowns, the element of the essential matrix, and each row in A is just resulted from one point correspondence. Okay, so like in the fundamental matrix case, we can solve this using the homogeneous least square solution using SVD. And since it has 9 entries, how many point correspondences do we need in order to solve this system of equations?
Should be 8, right? Because like you wrote, the scale is arbitrary, so it should be 8 points.
Yeah, so in general, without applying more constraints, we need 8 point correspondences. But since the essential matrix has 5 degrees of freedom, we will see that we can also solve it with 5 point correspondences. But for this case, we need 8 point correspondences. And then we need to verify that this essential matrix is valid. So we need to verify that it has a determinant of 0 and that its two non-zero singular values are equal. So how can I do that? I have an essential matrix and I want to verify that it satisfies my constraints.
You could also use SVD to remove the third singular value, to set this third singular value to be 0, but I think it's, I don't know how to deal with the equal singular values.
Yeah, so I mean, it's true. What we can simply do is to average the current two singular values and use them as the identical two singular values. And then rebuild the essential matrix from the singular vectors and the average singular values. So that's one solution, but the scale of the essential matrix can be set arbitrary. So we can just assume that S is 1 and use capital S to be a diagonal matrix with diagonal elements 1, 1, 0.
But why can we set the singular values to be like an arbitrary number?
Yes, we can.
Wanted.
Yes,
But
it's
why?
just yeah, it's true. It's just this solution will be the closest projection algebraically to the essential matrix, but you can just choose any number here, basically. Usually you choose 1 because it simplified the next steps, as we see in the next slides, but you can choose any number that you want. This is just the projection to the closest essential matrix.
Yoni, you're trying to find E, right?
Yes.
So if you're trying to find E, how do you do SVD to E if you don't have E?
If I don't have E? No,
Yes.
here I have an estimation because I saw the linear least squares solution. I had 8-point correspondence set or more. So I had this A matrix. All the elements here are knowns from my point correspondence set, and I don't know V. But I solve V using the homogeneous least square solution, and then I reshape it to be my solution for the essential matrix. The problem is that this is not an essential matrix. It might satisfy my equations, but it's not satisfying my constraints for being an essential matrix.
And one more thing, if you are taking 8 points, you will get 8 rows, right?
8 rows for A, yes.
Okay, thank you.
Then V is just a null space of A in this case. You will not have error at all. You'll just get a single solution in this case.
Do you try to prevent the solution from being the trivial solution of just all zeros?
Yes, when you solve the
As we
homogeneous
did last time?
Yes, well, actually, when I say that we solve the homogeneous least square problem, I mean that we minimize the norm of AV such that the norm of V is 1. So it cannot be zeros.
Okay, thanks.
Okay.
I have another question about that choosing singular values arbitrary. You only change the singular values, right? You leave the U and V on this slide, yes, the same.
Yes.
Okay.
Yes, I just keep the singular vectors.
How can you leave them the same? Because the dimensions here change, no?
Yes, so after you zero the third singular value, so you still have a rank 2, even if you keep the original singular vectors. So basically, you can just use 2 singular vectors after this. But you can keep the original structure and it will give you the same solution.
So you use partially columns from V and U?
You can use it or you can keep it and it will not change the solution.
Okay.
Again, why we don't have to have the 2 singulars value the same?
There is a proof for that. Because that you have a cross product matrix multiplied by a rotation matrix, this spatial, if you take general skew symmetric matrix, 3x3 skew symmetric matrix, and multiply by the rotation matrix, you can prove that this matrix will have 2 identical singular values. It's just
so this. Sorry.
No.
So this constraint is just like to make sure that we get the right essential matrix, right? And
Yes.
we cannot just use that the determinant is 0. This will be not enough.
Yes, that's important for you to be able to extract the rotation and translation later. Otherwise, it's not an essential matrix, and you cannot make sure that you extract rotation and translation and solve the original calibrated structure for motion problem. Okay, so let's do some like a short summary for the 8-point algorithm. We have 8-point correspondences from the original image. We normalize them with the calibration matrices to get yi bar correspondence for each I. Then you form A using yi's and solve the SVD problem, the homogeneous least squares problem using SVD. And then we form a valid essential matrix by ensuring that the determinant of E is 0 and it has two non-zero equal singular values. And then it is possible to extract a pair of cameras from the essential matrix. We'll show it next. And then we can actually get a solution for our original structure for motion problem, and we can triangulate 3D points from the solved cameras and the original correspondences. Okay, so that's the steps of the pipeline for using the 8-point algorithm and solve the calibrated structure for motion problem. So let's see an example. You see I marked here with same color as point correspondences from the fountain, and I calculate the essential matrix with the 8-point algorithm. So you can see just the numbers, they are not so far from the ground truth essential matrix. And qualitatively, if I map each point on the left side to its corresponding epipolar line on the right side, you see that the epipolar line passes through the corresponding point. So this is just an example. And now let's talk about the 5-point algorithm. That was published by David Nisser in 2004. So now we have 5-point correspondences. So we have 5 linear equations for E that are expressed with the multiplication of A with V, that should be 0. So what are the dimensions of A in this case? Can someone remember? I mean, each point correspondence give us one equation, right?
5 by 10 by 9.
Yes, exactly. A is 5 by 9. So in this case, we actually don't have a single solution for E. We have a solution for the equations up to 4 degrees of freedom as the dimension of the null space for A in this case, right? Because we have 9 columns and 5 rows. So we have 4 degrees of freedom for the null space of A, where V should be the null space of A. Okay, so we actually have a decomposition for E to a linear combination of 4 known matrices that are the reshaped version of the 4 vectors that span the null space of A. And we don't know the coefficients. We can just for now choose them. For every coefficient, we get a correct solution for our 5-point correspondence. Okay? Until now, it's clear, right?
And how do you find X, Y, Z, W?
Okay, that's the next bullet. But okay, so how do we find them? Because we know that we cannot, we need to, 5-point correspondences should be, should constrain enough the essential matrix. So one thing is that we can choose the scale factor of E by choosing delta to be 1, for example. And then we still have 3 degrees of freedom. So what we know about the essential matrix that we can use here to constrain the 3 degrees of freedom?
Maybe we can use the determinant.
Yeah, so we have the determinant, but we have what we also have that the 2 singular values should be identical, right? So we have nonlinear constraints on the essential metrics. So we can actually use these constraints to constrain alpha, beta, and gamma. We just apply them on the essential metrics. So the determinant is easy to apply. We know how to calculate the determinant of the metrics, but satisfying this constraint is more complicated, and I don't want to go into details about how to extract the equations for this. I'll just say that it is possible to extract a polynomial system for alpha, beta, and gamma, and it has 10 complex solutions. This system.
Yanni?
Yes.
How many degrees of freedom this equation that determinant of the essential matrix equals 0 will like?
The determinant of A equals 0 is give you 1 degree of freedom because it's just one equation on the 3 unknowns. And from the 2 identical singular values, you get the other 2 degrees of freedom. But it's not just 2 equations. You actually get 10 equations from this that are linearly dependent and not linearly, they're just dependent. And then you should you use them to extract the 10 complex solutions from this system. Okay, but
what do you mean by complex solution?
I mean that you always get 10 solutions. Like for if we have a polynomial of one variable with a degree of 3, then you always get 3 complex solutions. But sometimes you get only one real. You can get either 1 real solution or 3 real solutions, but you always get 3 real solutions, 3 complex solutions. So here also you will always get 10 complex solutions, and some of them will be real. So if you compute the essential metrics by the 5-point algorithm, you should only consider the real solutions. So you don't know how many real solutions you will get, but it will be at most 10, because there are always 10 complex solutions for this polynomial system. Okay.
There's no lower bound, right? Maybe all the solutions are complex.
No.
Or am I mistaken?
So so I don't know about the proof of a lower bound, but usually if you have like a setup that is physically correct, you will get some real solution. But I don't know of a bound, of a proof for a bound for this. Usually you get between 4 to 6 real solutions, but that's something from trial and error. I don't think that there is a bound. There might be, but I'm not aware of a bound for the number of real solutions in this case. Okay, but this is very useful because usually we use robust estimation to estimate the essential metrics, and we'll talk about it next week, I think. Renan will talk about it, but in robust estimation, the most popular method is ransack, where we use samples of point correspondences to constrain, to find a minimal solution for our model. So the chance to sample a good solution is much larger if you need to sample 5 good correspondences compared to the need of sample 8-point correspondences. So the ability to extract model with only 5-point correspondences is very important. But we will discuss it more next week. So it's just a side note why this is a very important algorithm. But I just wanted to show you one specific example for that. So here I used the 5-point algorithm to calculate the essential metrics. And you can see that the solution in this case is very close to the ground truth. And if we measure the algebraic error of the ground truth from our estimated essential metrics in terms of Frobenius norm, you can see that in this particular case, I got much larger error by using the 8-point algorithm compared to using the 5-point algorithm.
Yoni, so, and this is basically because of ransack. I thought that when you have to sample 8-point correspondences, it's just a matter of time. Like,
yeah, so I fixed the number of samples in this case. That's why. I mean, if I could have sampled like as many iterations as I want, then I would have probably get the same solution. But since I fixed the number of ransack samples in this case, I got better results from the 5-point algorithm.
Can we consider this structure from motion problem solved? Like, this is the best we can do in this case. So if we have 2-point correspondences, you just showed that we solved this problem, right? Or there are like deep learning methods that somehow perform better or something like that.
Yes, we showed last week. I mean, robust estimation is not a solved problem. It's very hard to deal with some noise patterns and noise ratios, large noise ratios, and you saw that it can be improved by better weighting of the point correspondences. The 5-point algorithm and the 8-point algorithm are just closed form solutions, so I don't see how they can be improved. Yes, I think the importance of the essential and the fundamental matrices is just they can be used to constrain the structure for motion problem for N views, for general N views. You have like hundreds or thousands of cameras. So usually you will use the essential or the fundamental metrics to give you some building block for estimating and solving the complete structure for motion problem. And that's a larger challenge. Okay, maybe let's take a break of 10 minutes and then we will talk about how to extract the cameras from the essential metrics.
Yoni, please pause the record. Just pause, not stop.
Yes, okay, resume recording. Okay, so now we'll talk about how to compute cameras from an essential matrix. So we estimated the essential matrix, but we don't know the cameras. And so as we talked before, we can assume that P1 tilde is identity and 0. So what we need is to find P2 tilde of the form RT such that the essential matrix that we have can be expressed by the cross product matrix of T multiplied by R. So that's the task of this part. Okay, so first, what we do is again apply SVD as usual, and we get the following SVD decomposition where we set the scale of the essential matrix such that the two identical singular values are both 1. Another thing that we want to verify is that the determinant of UV transpose is 1. Just help us later for proving the decomposition. And it is always can be verified by multiplying the essential matrix by -1 if it's not the case. Let's see why. Because if the determinant of UV transpose is -1, by the way, it's U and V are orthogonal matrices, so their determinant should be 1 or -1, right? For each one. Okay, so if it's not the case, we apply minus on the essential matrix, and then the singular value decomposition has the following form when we put the minus before the V. And then the determinant of U multiplied by the new V, which is minus V transpose, is just the determinant of minus I multiplied by the determinant of UV transpose. So the determinant of minus I is just -1, and we know that the determinant of UV transpose is -1 because that's what our assumption. So bottom line, we can always verify that this is the SVD decomposition of the essential matrix and that it holds that the determinant of UV transpose is 1.
Johnny, can you explain again why are we doing this? We already we found E. We verified that the determinant is 0, that the singular values are the same. Why do we do that?
So after you did it, you still could choose an arbitrary scale and a sign for the essential matrix. So now, as a pre-process, we just set the scale and the sign of the essential matrix. Okay, we will see later why it is needed for the decomposition.
Okay.
So next, we define the following two constant matrices for every decomposition, which we will use. So it's just these two fixed matrices, where W is a rotation matrix and Z is a skew symmetric matrix, which is easy to see because of the minus sign for the off-diagonal elements. But anyway, this is a skew symmetric matrix, and furthermore, if you just multiply Z by W, you get a diagonal matrix where its diagonal elements are 1, 1, 0. And Z multiplied by W transpose is also a diagonal matrix with 1, 1, 0 with a minus sign. So it's -1, -1, 0. Okay, it's just, you can just multiply the matrices and see that it is being satisfied. Okay, so we will use these matrices for our decomposition. One second. Okay. So using what we have written here, we claim that if the essential matrix has the following singular value decomposition, then there are two possibilities to decompose the essential matrix to a skew symmetric matrix times a rotation matrix. So you can see here, so you can see here the two possibilities. One of them uses S1 multiplied by R1, where S1 is a skew symmetric matrix, R1 is rotation matrix, and these are the forms of S1 and R1. And the second option is using S2 and R2, where S2 is defined as follows and R2 is defined as follows. Okay, so that's our claim, and we will try to show it for S1 and R1. What we need to show is that R1 is a rotation matrix, S1 is a skew symmetric matrix, and that S1 multiplied by R1 is a decomposition for the essential matrix, so we get the essential matrix. So how can we show that a matrix is a rotation matrix? What do we need to show?
The determinant is 0, and the dot product between its columns is 1.
Yeah, the determinant is a 1.
1, sorry.
Yeah, yeah, I realize that you're trying to say it's 1. So let's first show that R1 transpose R1 is an identity matrix. So we write R transpose here, R1 transpose here, and R1 here. Now the transpose of this matrix is just a VWU transpose. So we have this expression, and now U is an orthogonal matrix. So U transpose U is just identity. W, as we assume, as we showed, is a rotation matrix. So it's WW transpose is identity, and VV transpose is again identity because V is an orthogonal matrix. Okay, so it's just trivial to show that R1 transpose R1 is identity. And then we need to show that its determinant is 1 and not -1. So we write R1 inside the determinant, and we can, that equals to the multiplication of the 3 determinants. Now, W is again a rotation matrix. so its determinant is 1, and we already showed the sign such that a determinant of UV transpose is also 1, so we got that the determinant of R1 is 1 as required. Okay, so what do we need to show in order to prove that S1 is a skew-symmetric matrix? Someone remember what's the definition of a skew-symmetric matrix?
Should
Okay.
be equal.
So,
The
sorry?
transpose should be equal to minus that
The matrix.
the original matrix. Yes.
Exactly. So let's show that. We just put the element of S1 in and transpose it. So we get minus U Z transpose U transpose. So now we use the fact that Z is a skew-symmetric. So instead of Z transpose, we write minus Z. And now the minuses are canceled here, and we get just minus S1. Okay, so this is also, we showed that S1 transpose equals minus S1, so S1 is a skew-symmetric matrix. And then we need to show that S1 multiplied by R1 is a decomposition for our original essential matrix. So we write S1 and R1. Again, we get U transpose U, which is identity here. And then we are left with this expression. Now, as we talked before, ZW transpose is just minus diagonal of 1, 1, 0. So the minuses are canceled, and we just get the essential matrix. Okay, so we showed that S1 R1 is a valid decomposition for the essential matrix, and we can show it similarly for R2 and S2. Now, in the book of Hartley and Disserman, they proved that these are the only two possible decompositions for the essential matrix that satisfy skew-symmetrics times rotation matrix. Okay. So it's a bit algebra, but I don't think that's too much complicated. I hope that you followed, and let me know if you have any questions about this slide. Okay, so now we have a decomposition, but we want to extract T, right? So we have the cross product matrix of T. This is the skew-symmetric matrix, but we still don't know what T is. Okay, so how do we find the T vector that its cross product matrix is the matrix that we have? So we have the cross product matrix, but we want to have T. What can we do for extracting T?
This cross product matrix is like a one-to-one correspondence to a vector. No, we can just look at by the construction. We can look at the elements and.
Yeah, that's right, and it's and just for what you say is right. We can also use the null space of the cross product matrix, because if you multiply the cross product matrix by the vector that creates it, it's just a cross product of the vector by itself, which is 0. And so it is easy to show that the null space is given by the third column of U, because we know the expression for this cross product matrix. So it's just U3. Let's see that. So if you multiply this UZ U transpose, which is our cross product matrix, with U3, we get UZ U transpose U3. And then we multiply U with U3, so we get U1 transpose U3, U2 T transpose U3, and U3 transpose U3. But U is an orthogonal matrix, so we get 0, 0, 1. Okay, and then we have this matrix multiplied by 0, 0, 1, and it's just zeros because we have 0 times this column plus 0 times this column plus 1 times zeros column. So we have just zeros. So U3 is just a null space of this matrix, and we can just use U3 as our T vector. But okay, so we have two decompositions for the essential matrix, but now that we have them, we can still choose the sign of T, right? We are not limited anymore. We did not set the sign yet of T. We just set it for extracting two decomposition, but we still have two possibilities to choose the sign of T. It can be -1 or +1. Okay, so actually we have 4 ways to extract cameras from an essential matrix. Because we had 2 ways before, and we have additional 2 ways to choose the sign of T or of U3. Okay, so if we sum up everything, we have the essential matrix, we have the singular value decomposition, we have the W and Z matrices, and we have P1 tilde. Then there are 4 possibilities to extract P2 tilde.
Yoni, I have a question about this
Yes.
sign. So when you set the different sign for T, like this will change the relative position of the first camera and the second camera, right? Like, because if you have a plus sign for T, it moves to the right, for example, and if the -1, it moves to the left of the first camera. And those both will be 2 valid reconstructions for the scene?
Yes, because you will be able to get the original essential matrix by just using your P tilde reconstruction. Your solution for P2 tilde and P1 tilde will be consistent with the essential matrix. It will match all the point correspondences. And if you triangulate 3D points, they will be projected exactly to your 2D correspondences observation if you don't have noise. So it's a completely valid solution in terms of all what we know about the point correspondences. We will see next how we choose the right solution. But in terms of the projection or the solution to the structure for motion problem, the calibrated structure for motion problem, all 4 solutions are valid, completely valid.
But for example, like as humans, we can determine whether the second camera was like on the right of the first camera or on the left. So there's
yes, there is a way to set this, but not in terms of our original formulation, right? In terms of our original formulation for the structure for the calibrated structure for motion problem. Let's get back to this formulation. Like, oh, too much. Okay, both your decompositions will be a valid solution to the 2-view structure, calibrated structure for motion problem. You will get a 0 if you have no noise. You will get a 0 error by the 4 options. Okay, if we just consider the definition of the problem. Now I will show you how we can choose the right solution, but I just want to say that if all 4 possibilities are valid in terms of the problem formulation.
4 are valid, but only the 1 is correct.
Yes, right? Only 1 is correct. Yes. And it will still be defined up to similarity transformation. You can always move everything or scale everything or rotate everything, but you need to choose to first choose the correct decomposition in terms of the 4 possibilities. So just to mention that geometrically, the relation between UWV transpose to UWT UW transpose V transpose, which are the 2 R options, is just a 180 rotation around the line that connected 2 cameras. It's just something We will see in the next slides the visualization for this, but this is what it means geometrically. Okay, so let's see what we get. We have an upper view for our 3D scene and the cameras. So this is one camera, it looks to this direction. Second camera, it looks to this direction. Some of the triangulated 3D points are here, some of them are here. It doesn't look reasonable. But if I project the 3D points, I get a projection to my corresponding points. So it's a valid solution, but not correct solution. So this is option 1. Option 2, with the minus sign. So still this camera looks to this direction, this camera looks to this direction. And in this case, the two cameras are looking on the 3D points. And you can see a top view of this fountain. This is the pool and the wall. Okay, it's just a top view of the scene. And in this case, the object is behind the cameras. Oh, they're looking to this direction. Okay, so what is the correct solution in this case? Which option?
Will this always be the case, like that the option 3 is the correct one?
You need to verify all 4 options and then to choose the right decomposition. So, but you can always do that. It's very simple. Like you don't have to look. You can do it automatically. Can someone think of a way to choose the right solution automatically without looking on the results? What is the depth of the points in each case? For with respect to the cameras. So in this
It will be positive.
Yeah, so in this case, the depth of all points in both cameras will be positive. In this case, all the depths will be negative, right? Because the object is behind the camera. And in this case, it will be splitted. About half of the points will be in front of one camera and half of the points will be in front of the second camera. So you can just choose the solution with the maximum number of points with positive depths. Okay, we will practice it in the next exercise that I think we will publish today. So it's very simple. You just need to implement it and you will see. But it's practically it's not a problem. You just consider all 4 options and choose the correct one automatically. But it's nice to look what geometrically the options are. Okay, any questions about the calibrated structure for motion problem? Okay.
About U and V, it was really early in the slides where you use the SVD decomposition and then you defined E with the average of 2 singular values.
Okay.
And you just used the U and the V. No, it wasn't this slide.
The projection to valid the essential matrix.
Yeah, I'm sorry, I'm taking you so behind. Yeah, this. I'm not sure exactly where I get U and V from. From the SVD, like copy paste. This is the exact matrices.
Yes. It's just give you this solution give you just the closest solution to the closest valid solution to your estimated solution in terms of Frobenius norm. Just a projection. Because you get a matrix by considering the point correspondences, but it's not a valid, it's probably not a valid essential matrix. So you just want to project your solution to the closest element in the set of valid essential matrices.
Yeah, I understand the problem, but not so much the solution itself. I mean, U is M by M, S is M by
No,
N, and V is
no,
M by
no,
N. So
it's a 3x3 matrix, right?
yeah.
So you get a 3x3 U, 3x3 V, and a 3x3 S, which is a diagonal matrix.
Oh, okay. So when you construct S again, it's 3 by 3 and it doesn't change the dimension.
Yes, you just get rebuild this 3x3 S matrix, and you just 3x3 times 3x3 times 3x3. But you can use here 3 by 2 because the third singular value is 0, and it will not change the solution.
Okay.
And 2 by 3 here.
Can you also explain again when you're trying to figure to do with 5 equations? How do you find X, Y, Z, and W, the span of E?
Yeah, so let's look at the A matrix here. So you have a linear system of equations. A multiplied by V is 0. Okay, so you're actually looking in this case for the null space of A, right? The vector that zeros A. But A has only 5 rows and 9 columns. So the dimension of the null space is 4 in this case. It is spanned by 4 vectors. Each vector is a 3 by 3 matrix actually, because we reshaped the 3 by 3 essential matrix to a vector of 9 elements. So each vector that is used to span the 4-dimensional null space is a 3 by 3 matrix. So that's what I meant when I say that we have 4 3 by 3 matrices, X, Y, Z, and W. Each of them, if you flat it to be a vector, is a vector that is in the null space of A. And all 4 of them will be independent and span together the null space of A in this case. Does it answer your question?
Yes, and again, how do you find A, B, and gamma?
You just apply the things that you did not use yet. For now, you just used the point correspondences. So any solution in this linear combination will be in the null space of A. So you already satisfy the point correspondences constraints. What you did not use yet is that the essential matrix has 2 additional properties of determinant 0 and identical singular values. These are nonlinear properties. So if you want to apply them, you get a polynomial equations, system of equations. So I think Ronen might talk about how to solve polynomial system of equations next week, but I'm not sure. We can ask him later. But there is a large field in computer vision about how to solve polynomial systems and this is one of the examples that you want to use a solver for a polynomial system.
In the next assignment, we're going to do it with 8 point or with 5?
I think that in the assignment 3, you will use the 8 point and not the 5 point algorithm. Yes. But it is implemented in MATLAB and in OpenCV. So you can always have the solution and you can read the paper if you want. There are a lot of minimal problems in computer vision. For example, there is a minimal problem when you want to estimate also the focal length of the calibration, if you assume something about the calibration pattern, and there are a lot of minimal problems. We also have published a paper about a minimal problem for solving camera poles from 2D correspondences between multiple views and to solve the camera metrics of a new view. So just a very large field in computer vision. But here I just talk about the 5-point algorithm. Okay. Okay, let's talk a little bit about this paper from 3 years ago, published by Melekov et al. And in this paper, they try to estimate the relative pose between two cameras directly, without point correspondences, okay, just from the images. And the motivation for not using point correspondences is that sometimes point correspondences are very sensitive to properties of the scene or the cameras. For example, if the angle between the camera is very wide, it's very hard to find point correspondences. And also, sometimes some of the inliers are very concentrated, so they do not constrain the solution enough. And you can get a solution with some outliers. And also, in order to have point correspondences, you need to have a constant color that is invariant to the viewing angle. But sometimes there are some reflectance properties in the scene, and you get a very different view from the different views. You get very different images, so it's hard to find point correspondences. So this is a general limitation for point correspondences. And they asked, why not just use the images and use deep learning to regress directly the relative camera poses from the images? Like, we know that deep learning works well for images. Let's use it to extract relative camera poses. Okay, so that's what they try to do. And for representation, they use the 7 vector with 7 elements, vector in R7, where the 3 entries of this vector represent the translation vector, and 4 elements represent the quaternion, where quaternion is just a way to represent rotation. There is a direct map from a quaternion to rotation matrix. It's just representation, so I don't want to get into too much details about how to represent rotation with quaternions, but let's just assume that given 4-dimensional normalized vector, I can map it to a rotation matrix. Okay, so this is their representation for the relative pose between two cameras. Okay, so let's look at their architecture. It has 3 parts. The first part is Siamese network architecture. It means that we apply the same convolutional set of layers on each image independently, and then we extract feature map from each image. And the architecture of these convolutional layers are just the same architecture as in AlexNet, without the fully connected layers. So that's the first part. Then, let's see, how much time do we have? Okay, I'll just say briefly that sometimes people crop and reshape inputs for a neural network in order to have a fixed size of outputs from the convolutional layers, because fully connected layers need a fixed set of inputs. Okay, so, but this sometimes results in a very distortion input to the network, so it's not easy to generalize in this case. And instead, they use what is called the spatial pyramid pooling, SPP layer, published by Kai-Ming He et al. 7 years ago. And the idea is that instead of pooling like regular pooling, they split the image into a grid with a fixed size, and then they pull from an image a fixed size of elements. Okay, so for example, if I use 2x2 grid, then I will just get 4 entries with the same dimensional of the feature map that I had before. So it's invariant to the image size. No matter what the image size, I will always get 4 outputs from this 2x2 grid with 256 dimension. And in this case, where we used 4x4 grid, I'll get 16 outputs. So just a way to control the number of outputs given images with a given set of features. And that way, it is possible to feed fully connected layers with a fixed number of inputs, no matter what the size of the images that we put into the network. Okay, so and then they use 2 fully connected networks. One of them calculates the translation, and one of them calculates the rotation. Okay, so that's what they use. Any questions about their architecture?
Can you explain again about the SPP? Why is in the end and not in the beginning of the network?
No, I mean, convolutional layers are, you can put any images inside, right? It's just apply on patches. But fully connected layers has a given set of size. So they wanted to apply the same convolutional layers, but to get a fixed size of output and still be able to use large images and small images. We will see next how they train the network, but if your training set has different size of images, then you need to handle it somehow. So that's how they handle it.
Cool.
Okay, so they use the supervised approach to train the neural network. They have a ground truth, T hat, and a quaternion hat. And they just regress the output to be similar to the relative ground truth translation and the ground truth relative rotation. And they had some and T hat and quaternion hat are normalized beforehand to have norm of 1. Quaternion always should have a norm of 1, and they just set the scale of the 2 cameras to be 1. So they set the relative translation scale to be 1. And beta is the rebalancing factor between the rotation loss and the translation loss.
Yoni,
Yes.
how do they set the norm to be equal 1 in this?
They just normalize the ground
training.
truth. You mean the output of the network? Yes. Okay. So the ground truth is normalized by definition. They just normalized it, and the output of the network is not constrained to be normalized, but they just do it at the post-processing. Just normalize it after it is outputted from the network.
Okay, and this is a differentiable operation, so we can.
Yes, exactly.
Properly.
Okay, so for training, they use pre-trained weights for the convolutional layers that were tried on classification tasks for ImageNet and places. And they, for training their main pipeline, they use the public image collections of landmarks, like the following tourist places. And then they applied the SFM pipelines that consider all the images together and treated them as ground truth. So these are just images that were taken by people that went to a vacation, and there is public collection of these images with a good estimation for their camera poses. Okay, so they use this as ground truth, and they use the first 5 scenes as training set and the 6th scene as the validation set to train their network. And they evaluated it on a very different setup with the DTU dataset for object scanning. So the images look like the following examples, and each scene has between 49 images or 64 images with specific set of relative poses. And they also split the DTU dataset to a training and testing set in case that they wanted to train on the DTU also. Okay, so let's see some results. What we see here, the y-axis is the ratio of the pairs of cameras. and the x-axis is the degree, the rotation errors in degrees for this plot. And the point here means how what's the ratio of cameras that they were able to regress with an error that is smaller than the x value. Okay, so I want this kind of shape to have all my points with a 0 error, but in this case you can see some pattern about the errors, some distribution for the errors. So for example, the blue and green curves are for the classical method that use point correspondences, and these 4 curves are the outputs, the results for the convolutional neural network outputs. And as you can see, the classical methods can get very accurate results, but only for a small fraction of camera pairs, probably pairs where the viewing direction is very close. But when you consider a variety of viewing directions, then they get very non-accurate compared to the deep learning solution, which is more stable. So if we look at more deeply, ORB features with which are measured in the green curve are less accurate than the SURF features. By the way, I'm not sure why they did not use SIFT feature correspondences. SURF with high resolution is performed most accurately, but again, not so accurate on challenging cameras. And they have some differences in the CNN outputs, in the convolutional neural network outputs. For example, if they did not train on DTU, they get the gray curve. But if they train on DTU high-res and apply on high-resolution images, they got the yellow curve, which is their best performance. And for the relative translation, they show the same plot. In this case, they also measure degrees, which is just a degree between the normalized translation vectors. So there is a ground truth translation vector and their output translation vector, and both of them has a norm of 1, so it just measures the angle between them. That's the error. Okay, but if they apply on cases where point correspondences usually fail, they got much better results, where there is a challenge in texture or reflectancy. So you can see that in this case, they got a better shape compared to the classical methods. Let's see some visual results. In this case, the baseline completely failed. And you can see the correspondences that it got, like this correspondence between its nose and the top of the skull, which is completely wrong. But their deep approach got only 52 degrees of error. By the way, I think that this is also a failure. It's not so accurate, but 52 degrees of error is not so accurate. Okay.
Why is the
Yeah.
translation in degrees?
That's why I try to. What they measured, you have a relative, you have translation vectors of the ground truth and their outputs. So both of them are normalized to have norm 1. So you can just measure the angle between them. The idea is that you cannot set the scale, so you just measure the angle between the estimation and the ground truth. Right? You have 2 vectors that you want to compare.
Okay. Yeah.
Okay, and here's another example. In this case, both methods more or less worked. And in this case, the baseline worked better than the deep approach. Where the viewing angle is much low, with the viewing angle difference is much negligible. Okay, so to sum up, we talked about how to compute cameras from the fundamental metrics, and we talked about the essential metrics. how to estimate it with the 8-point algorithm, the 5-point algorithm, and how to compute cameras from the essential metrics. We talked about a deep learning method that predicts relative motion. We saw that it is still limited. And next time we will talk, Renan will talk, I think, about robust model fitting. Okay. So any more questions? Okay. So we'll meet next week.